Hello everybody. In this video we're going to be looking at the following problem. This was one of the weekly challenge problems on brilliant.org under intermediate. So not too easy, not too hard. Let's see if we can do it. How fast in meters per second does a spaceship need to orbit around Earth to not spiral down, so to not go like whoosh and crash into it, and not fly away from it, you know? We want to stay in orbit. And from what it seems here that, you know, just from the picture, instead of a normal orbit, right, where like something normally that would orbit around the sun, right, it would go in an eclipse orbit, an elliptical orbit. And that's I I I believe Kepler's first law, I want to say, is that orbits are elliptical, or at least for planets around suns, but I think moons around planets also holds. But since we sort of have control over our orbit, in a sense, we're going in a circular orbit just around the Earth. And so we have details and assumptions. So the spaceship is 400 kilometers above the surface of the Earth, and the Earth's radius is 6,371. So that puts this total length at 6,771 from the center of the Earth to the spaceship. And we're given that the gravitational acceleration is 8.69 meters per second squared towards the center of the Earth. And so once you realize that this will be a circular orbit, right? And since the radius isn't changing because it's staying at 400 kilometers above the Earth, and the radius of the Earth isn't obviously changing, assuming it's a sphere. I know it's not a perfect sphere, but assuming it's a sphere. And so we want to find the constant velocity that will allow this to occur. And while we think if we have constant velocity, that means this is uniform circular motion. And in uniform circular motion, there is acceleration that is towards the center of the circle, right? And that's called centripetal acceleration. And you might think, well, I mean, unless you already knew this, but if you don't already know this, you might think, well, how can there be acceleration if the velocity is constant? Well, acceleration, it's a change in the velocity vector, because a vector has two components, length and magnitude. Or, sorry, length and direction. Um, and so if the length of the velocity vector isn't changing, then the centripetal acceleration will change the direction, right? And we notice that sort of if we take a point on this circle, the velocity vector will be tangent to the orbit, the circular orbit. And so it's keeping the same length, but it's going around the circle, so that's always tangent to the circle. And so if you use those facts, you can actually derive that the formula for centripetal acceleration is the velocity squared divided by the radius, by which, you know, the radius of the circle. And so since the acceleration due to gravity here, it's pointing towards the center of the Earth, and we're assuming that's the only acceleration on the spaceship. So that has to be the centripetal acceleration is 8.69. And we want to solve for v, so what we can do is just multiply this by the radius of the Earth. And then we have to be careful here because our radius is in kilometers, but everything else, our acceleration is in meters, and our velocity is in meters. So we have to multiply by 1,000 to fix that. And so now this is equal to velocity squared. So you have to take the square root of this, and this is equal to the velocity that we need. Uh, so I don't have a little calculator thing, but uh, I, I guess symbolically the answer is that v is equal to the square root of a times r, where obviously you have to have r in meters. Um, so anyway, I hope you enjoyed this video. I just want to show that I actually first saw this problem and I was like, oh man, is this rocket physics? And I actually put some thought into it and I was like, no, it's just uniform circular motion. So, sometimes physics problems look harder than they really are. So anyway, thank you for watching and I'll see you in the next one.